Ah, Michelle has changed her avatar again. I think it's daily, right? It's good afternoon. Good afternoon. I'm waiting for the Pokemon one though. I mean, come on. Yes, LOL. All right, awesome. But can't there be one Pokemon one? Just one. I mean, I know the whole world is overwhelmed with Pokemon, but all right, no, yes, I'm just kidding. Good afternoon. Okay, I'm saying well, oh, that's funny. All right, good afternoon, Yavi. Oh, good afternoon, Cheska. All right, Cheska wins the award today for awesome. And Melina, good afternoon. Okay. Good afternoon. Yeah. Oh, yeah. All right. Thank you, Michelle. Oh, all right. Okay. Good afternoon. What am I? Okay, I'm getting myself confused already. Good afternoon, Yavi. Good afternoon, Michelle. Good afternoon, Cheska and Melita. Good afternoon, Amanda. We cannot start. Look, it takes me 5 minutes to say hello as it is. Good afternoon, hi you. I mean, excuse me. Good afternoon and happy lunch, Chris. Good afternoon. But there's Michelle. All right. Good afternoon, Michelle. Excellent. Thank you. Good afternoon, Matthew. I think I did not say good afternoon, Avani. Good afternoon, Melita. That's funny, Amanda. Oh my God. Wow. She's paying attention. See this class. I'm gonna remember this class. You guys definitely, that's multiplayer co-op right there for Amanda. But anyway, all right. And good afternoon, Michelle. Oh, did I not say good? Wait. Oh, and yeah, right. Okay, Michelle. Awesome. Okay. And Amanda got, oh, and you can tell that it was Melita who got, oh, this is meta multiplayer co-op. Okay, that's gonna be a new portal if I remember, like multiplayer co-oping a multiplayer co-op, like with okay, that's funny, Chris. Okay, that is funny. That 10 miles from school. I don't even in New York, I don't even know what 10 miles means. I mean, I know what it means, but all right, anyway. All very hilarious. I do need to open more portals. Okay, we're gonna get to business. The business, okay, the business, if I live 10 miles from school. If I leave at 1:40, how many miles do you leave? Do you live if you okay? All right, Amanda. Oh my God. Wow. All right. Or as my brother would say, pachoo, pachoo, pachoo. Okay. Okay. Wow. Okay, Amanda's at these guys. All right, this is I definitely want to be in their lab group if they are a lab group. And if I want to I'm gonna shut up. All right, I'm gonna get drawn into this. I already am drawn into this. Very funny though. The agenda item, the big agenda item for today is the big old duck. That is the last problem. There's a problem called Big Old Duck, which is the last problem on a set of sheets called Big Old Duck Homework 6, right? And that's where this whole ship has been heading. It's the hardest problem, and I believe Big Old Duck is the most involved, challenging problem in that packet. That doesn't mean, I mean, some people did it fine. But it's definitely thick. It involves thinking. It puts together a lot of things. And Big Old Duck, here we go, is a transition, you might notice, is a transition from homework 6 to homework 7. It's a transition from one-dimensional problems, all of which our problems have been thus far. Everything we've been doing in lecture up till this point has been one-dimensional kinematics, motion in along one axis of space. Now, Big Old Duck is the beat in lecture that transitions us to how to do physics problems in more than one dimension. Of course, that's already happened to you in the lab. The transition in lab was lab 3, but then very specifically lab 4. When I start talking about Big Old Duck today, I hope you will see, I hope you'll see that Big Old Duck is like the lecture recitation version of lab 4, the ballistic projectile. They're very, very similar in many important respects, not the least of which is they bring our physics into 2 dimensions, which is the bulk of homework 7 is all about 2 dimensions. And once you can do 2, that is shorthand for higher than 1. I mean, once you can do more than 1 dimension, you can do more than 1 dimension. So we're going to get into Big Old Duck. We're going to start dealing now with 2-dimensional problems. And indeed, let me, and there's something in the chat, or maybe there's a lot of things. Sorry. Oh, that's funny. Right. Wait, okay, that is funny. I hope you do work together in the next lab switch, actually. I don't know. Okay. But or maybe even work together, as many of you should and will, when you are preparing for or even thinking through your exam, which you now will note has been announced in Google Classroom. We're not going to spend all day today talking about it. We're going to talk about it a little bit more each day. If I'm not careful, like entire classes can degenerate and get like taken over by exam concerns. So we're starting by I just want you to confirm with an electronic hand or something. Just confirm if you see that in Google Classroom today, an announcement was made regarding the basic. Oh, there's Yavi too. Hello, sorry. Oh, and Chris. Okay, good to see you. Good to see you. Awesome. Yes. Okay. So you see. Okay. So I will expand on many of the details. And I mean, that's already kind of a long posting. It's meant good. So you all see that the exam has been sort of announced. Details have some overarching details have been provided. I'm glad you see that. That Google Classroom notification will not. We will talk. We will expand on those details, and I'll answer questions and stuff. But I'm going to do sort of a little each class. I'm not going to take over this whole class on it. The basic facts to know, though, are yes, your exam will be take home. I mean, they are in physics. That makes it for a sort of a different kind of exam. It will be, what you need to know is that it'll be posted, not this coming Thursday, but a week from this Thursday. It'll be posted on Google Classroom no later than 8 p.m. on Thursday night, a week from this Thursday. And then it'll be due back right before class the following Monday. That's the key thing that you need to know is you have the full weekend to do it. And yes, it is open universe and untimed, and we will talk about that. Believe me, I know what that means even more than you think I know what that means. Maybe. But it's not timed. You have the full weekend to do it, but therefore you want to, and you can help each other, Amanda and Chris and other people. That you can, and you should know that it is legal for you people to help one another. Therefore, you would almost put yourself at a disadvantage if you didn't do some kind of communication with some fellow students somewhere during the process. You should, but you need, and we'll talk. So it's posted a week from this Thursday. It's due back right before class the following Monday. You do this, you have to be serious and firm about the deadlines and the rules because so many other aspects are very loose. You need to turn it in before 3:05 on Monday, October 30th. Right, October 30th. And then you need to show up to class. I will be re-emphasizing this as we get closer, but that's part. You just pretend you're taking an exam that day. Like you need to show up for the exam day. It's just that in your case, the advantage is you'll be breathing a sigh of relief when you come to class. And class is usually more relaxed on that day too. I know you'll be exhausted, blah, blah, blah. But you need to show up and the exam needs to be turned in time. And the bottom line to know about the exam is I know that you know that I know that it's take home and open universe. That means you have to write the exam with that standard in mind. I won't be looking for correct answers. I know you have the correct answers. I will be looking for thought process. You view the exam as a project or a presentation, if you like. You view it as a final copy of something that you have practiced and worked and drafted prior to that. You are giving me a demonstration, not of correct physics answers, but of why they are correct, like in effect proofs, derivations, and how you understand that they are correct. The whole exam is like a prove that you really get it kind of exercise. So the more colors, the more different, the more layout, like pictures over here, math equations over there, and then comments over here. You want to present it. You want to make it as readable and clear and comprehensive as possible. All the homeworks have been like a practice for that. Okay, I'm already saying too much about it. We'll talk more about it as we get closer. But as you also know, as it also says in Google Classroom, you'll see a practice exam before the real exam. The practice exam is like my draft copy of the real exam. It'll be very, very close to the real thing. There will be changes, but It will certainly address most questions that most people have about format or what's covered or what types of questions. You're just going to see the document before you ever get, or something very close to it, before you get the real thing. And yes, there already is an old copy of an old practice in our Google Classroom right now. You can already be consulting that for perspective, but that's an old copy. I will update that and make it more correct for your class by sometime by this coming Thursday. Okay, I've already said you, but that's the deal. All right, we'll talk more. Hopefully you'll have time also with that practice document. Hopefully you'll have time to address it and some solutions and stuff in the lab period. I will talk to him. I'll talk to Professor Walters. I can't guarantee that, but we'll see. But sometimes that happens. But again, the practice is for your practice. Oh, sorry. Is that I'm sorry.
Sorry, we have Professor Mercedes for them.
Oh, right. I keep doing that. I'm sorry. Right. So she does. Right. No, thanks for reminding me. So I'm in constant communication with her. She's always up for that. Like, it's just a question of logistically that we could, well, sorry, as long as you're saying that, Melita, too, could you just remind me, when do you have lab period with her? Like what day?
Wednesday, right after this class. So from 4:30 to 7:10 in person.
Wow, that's a long day. Okay. Oh, that's so. That's why many of you do this from John. Right. Okay. Thank you. Okay. So it wouldn't be today, but that you would do this. But ideally, and I'm not promising because it depends, like on logistics. But ideally, she'll give you time during lab next Wednesday to either work on the practice, or work together, or that you'll or get some solutions to it. Like usually there's some kind of address, like review time in lab, at which point you'll deal with the practice exam that you will already have had in your possession, for a week, like that you'll get by this Thursday night. So am I saying this right? Yeah. So you'll have lab the day before your actual exam is posted. That means you will have been working on a practice up until that point, and hopefully lab period will help cement all that. Hopefully this is all basically clear. We'll keep talking about it, but the idea is, the bottom line, and it says this in Google Classroom, even though this will rattle some of you very responsible students who have done all kinds of successful studying approaches to other science classes, in this science class, I am telling you the best way to study is not to study as such, but just practice the bejeebers out of the practice document. It's all about the practice document. The exam will be shockingly close to the practice document. It won't be identical, but it's not meant to be a trick. You want to use the practice document as your primary way of preparing for this exam. Like it gets more specifics but okay. It's like the reason to use Khan Academy or the MSRC or old textbooks or other people, the reason to use all those other resources is when you get to points in the practice exam when you realize, oh, I don't get this, I don't understand this. Then you look up a bunch of other places to try to understand it. But use the practice exam. Like, don't just randomly study things or try to memorize equations or whatever. Just try to nail the practice exam, and ideally do it 3 times. Again, but anyway, thank you, Malik. So you'll have it by this Thursday night. Again, there's already one that you could start working with, but it's like old, so it's not perfect. Blah, blah, blah. I think you all get it. Okay, Wednesday. Okay, Wednesday, right. Okay. And of course you could text and email me with concerns too. But okay, so why I'm saying all that is the big old duck very usually is one of the is like a very much an exam type problem. Almost always on the midterm, there's some kind of problem that's very much like the big old duck. And sometimes it's disguised. Like sometimes you have to understand the big old duck well enough to recognize that even if the whole problem, for example, is turned on its side, which sometimes it is, or even if the information you're given is different and what you're solving for is different, which sometimes is the case, the format of the big old duck is a classic exam problem. So we should get to it, of course. So here we go. But to that end, okay, so I'm going to say a couple things. We still have 2 threads that are going parallel in this class right now, and they're a little confusing to people. I mean, the fact that there's like 2 threads, 2 tracks along which our physics train is running, can be confusing to people. One track is just these one-dimensional kinematic definitions, concepts, and equations, just like velocity, acceleration, constant acceleration, free fall acceleration. That's one thread that is definitely part of the exam. I mean, it's a huge part of the exam. The other thread, though, is this whole nature of velocity itself, the relative character of velocity, i.e. Galileo's principle of relativity. Okay, now I'm promising you that those two things really are unified. I mean, basically one thread is kind of about the equations and the symbolism of how acceleration relates to velocity. And the other thread is velocity itself, what it really, really means when we think about it deeply. Both of those threads you need to have in your possession to solve problems correctly in physics, like for the rest of your life. But both those threads can seem a little disjointed right now. Right? They're going to start seeming more and more unified together, especially in homework 7. But what I'm going to say right now is they're also unified in the Big Old Duck and in lab 4. So before giving you you don't need any more equations to do the Big Old Duck. In fact, you don't need any more physics equations to do homework 7. You're done with the equations that need to be provided for you. And if you want a list of them, they're coming up in a second on the next page. But we're still pushing forward this concept, this new concept, this principle of Galileo's principle of relativity. So I'm going to tell you right now what's on the board right now that you need for the Big Old Duck and for the exam and for lab 4. What you need is, in fact, a 5th form of Galileo's principle of relativity. Now, again, I'm going to summarize the other forms in a second on another page. I know it's all new, but Galileo's principle is one principle, right? The larger principle that velocity is a relation between two objects. It is not a property of one single object. That is a fundamental idea in physics that so much is based on that even itself is said many, many different ways. I'm here to tell you that basically the rest of our courses are just different versions of that idea. You've gotten 4 of them already. The 4th is complicated and mathematical and has 3 cases. I'll review it in a second. Well, I'll remind you of it in a second. But I'm now going to tell you the 5th version of that idea. I haven't said this before in class. This is a new thing I'm saying. I'm saying here, Galileo's principle of relativity, GPR, form number 5 says, wait, is the board, okay, sorry, the board is blown up. Wait, 100%. Sorry. Okay, here, now I can fit. All right, the board says, form number 5, every n-dimensional physics experiment or physics exam problem is really n one-dimensional experiments occurring simultaneously yet independently. That's a new form of the same old idea of Galileo's principle. What do I mean by that? Well, we're going to see. But why am I even saying it? Why am I calling it a principle of relativity? Because the principle, if you remember the principle, now these are abbreviations here. I didn't write them all out. This is just reminders right here. You have them in your notes. But the principle, form number 1, is that the laws of physics are the same at all constant velocities. And put another way, in all perspectives. Put another, or unaccelerated perspectives. Put another way, the laws of physics are the same in all different coordinate systems. It doesn't matter if your coordinate system, your perspective, your way of measuring the world is going like this, or going like this, or going really fast like this. The laws are the laws of laws in all coordinate systems. They don't change from one to the other. And therefore we say, therefore you can't do an experiment to know which coordinate system you're in. You can't do an experiment to find out whether your coordinate system is sitting, whether your perspective, whether from your perspective you're actually sitting still or actually moving at 100 miles an hour. You can't do an experiment to figure that out because the laws are going to be the same and lead to the same experimental results regardless of what coordinate system you're in. So you can't use experiment to find out. And therefore, form number 3 at the bottom of the sheet says, therefore, since you can't find it out in experiment, and this is experimental science, I mean, this is physics, if you can't ever design or perform an experiment to find out whether you're actually moving or act at some speed or actually not moving, then there's no meaning to that at all. Then all we could ever find out is whether I'm moving relative to something else or something else is moving relative to me. All we can ever find out is velocity as a comparison between two objects. Therefore, that's the only meaning that there is to velocity, right? That's just a quick summary of the first three forms of the principle. But now what I'm saying, to help with Big Old Duck and to help with Lab 4, now what I'm saying is, well, wait a minute. If that's really true, if the laws are, oh, and then of course there's GPR4, which is like the mathematical version of this, right? But now I'm saying in GPR5, I'm saying, well, if that's really true, that the laws don't change from one coordinate system to the next, the simplest coordinate system I can imagine, is one axis, right? Like the x-axis, the number line, which was the basis of our entire homework 1 that we spent so long on, that's a coordinate system. That's a perspective on the world. It's just a perspective on one dimension of the space of the world. Well, if we really take Galileo seriously, we really take seriously the idea that like the laws are the same, whether you're looking at the world through a horizontal lens or through a vertical lens, then what that really means, if you think about it, is like this is physics, and the physics laws apply. So all those laws or those equations or those definitions that we derived and established from our first homework on, all our equations, and here they are, by the way. So this is a list, sorry, here's a list of all the equations that I think we have so far in the class. If you just, people have been asking for it like in one tidy place to help, which makes total sense. So here's one tidy place with all the equations that we have so far, written the way I write them. Obviously, other textbooks, everybody writes them slightly differently. You'll know that you're really getting good and comfortable with these equations if you're not super bothered when you see them appear in slightly different forms and you still recognize them. Sidebar. So here's a list of the equations you have so far if you're starting to prepare, and obviously this is in the PDF that I'm gonna, that you'll get at the end of this class. But these are the equations we have so far. They're all like one-dimensional equations. They're all about definitions and concepts that apply to velocity and acceleration and constant acceleration in one dimension. I will also say, there is something in the chat. I'm sorry, I'll go to the chat in a second. But I'll also say another place that these appear, because people have been asking, another place that these appear is on the inside, like on like page 3 or something of the old practice exam that is available in Google Classroom. Even though I'm going to update that exam for sure, whatever new exam I put in there will also have an equation sheet like this. It'll have other equations too, but it'll have an equation sheet like this. And that signifies to you that, yeah, you'll have a sheet of these to work with when you do the practice exam and when you do the real exam. So you don't want to spend too much time memorizing these things. That's not the point. That's kind of a waste of your time. The more you practice, the more you'll see that you don't really need to memorize them. The more you practice, the more hopefully you'll start seeing that they just make sense, that they're just English definitions, mostly expressed in symbolic form. But anyway, for those, so here's the equation. Oh, I should add one thing to this list too. I should probably say also, sorry, one thing to add to it. Oh, okay, yeah. Also to add, here's a piece of knowledge that in free fall, acceleration is a constant, and it's known as g, lowercase g, and g, at least the magnitude of it, is approximately 10. Here, I'll write it differently, actually. It is a piece of knowledge that we got, that g is approximately 10 meters per second squared. And I'm putting a plus or minus on that. You'll see we get to be, because that's also up to your choice of coordinate system. Like it depends whether it's always down, but whether you define down as negative or positive is up to how you solve the problem. So anyway, these are facts that you can, step 3 GDPs that you can use and will use in the exam. These are the equations that govern one-dimensional physics. But then what I'm saying here on the next page, in terms of concepts that we know, Form 1, Form 2, Form 3, Form 4. So it's all written here. You know, if you want a reference guide, here's Form 4, which we still need a lot of practice on. I'm very aware of that. Then Form 5, what I'm talking about right now, is saying, well, look, if the laws of physics are the same in any given axis, if all those equations that we've been spending a month and a half developing like apply to physics along a number line, then it shouldn't matter whether the number line looks like this or the number line looks like this. Those are the physics truths of one dimension. So it doesn't matter which way that one dimension is facing, the laws are still true. And therefore, here's my big point, and finally we'll solve the problem. Therefore, the key insight, a big key insight, is for us to transition in our understanding of one-dimensional problems to two-dimensional or three-dimensional, four-dimensional problems. The key thing is to not be intimidated by the presence of higher dimensions. When we look at the big old duck, so here we go with the big old duck. When we look, and then I will look at the chat. I'm sorry, it's probably something super, probably like it probably means there's 85 people in the waiting room and I'm muted and something, but I will look in a second. When you look at the big old duck problem, it's intimidating because for the first time in this class, things are happening along an x-axis and a y-axis. That you should recognize that that looks like a new thing. And same thing with lab 4. Like a bullet was shot, or a ball was shot out of a ballistic device and like went flying off a lab table, but then also fell down in some kind of arc toward the floor. That's intimidating. That's definitely a new scenario. But what we're saying here is, from here on in physics, we're saying, so what? This is physics, and this is physics. This is governed by physics laws, this axis, and this axis is governed by the same physics laws. So from here on in, if we observe or consider anything happening in 2 dimensions, what we're going to say is, oh, a 2-dimensional problem? Really, what that is 2 one-dimensional problems, each one of which can and should be solved independently. I.e., you do, like with lab 4, you look at what the ball's doing as it goes forward, regardless of what a ball would do when it's falling down. And then you look at what a ball does when it's falling down, regardless of the fact that it happens also to be moving forward. The x-axis does not affect the y-axis from here on in. And really, to understand that is just to understand that that's another extension of Galileo's principle, that the laws of physics are the laws of physics. They're not affected by axis or perspective or velocity. So anything that looks like a 2-dimensional problem, what makes it a 2-dimensional problem is that 2 independent 1-dimensional problems are occurring at the same time. At the same time. So what from now on, and this is true of all the vector stuff that you're being asked to do in homework 7, when you're asked to like break up vectors into, or like hypotenuses into like horizontal components and vertical components and stuff, the whole theory behind all of that is, as long as we can see what's happening on one axis and see what's happening on the other, we treat them completely separately. And then we just put them back together at the end of a problem solution. We put them back together just with the one recognition that they're occurring at the same time. So here's the duck problem. Here's the duck problem. This is my step 1 DFP. You definitely, someone else asked this in the other class, for sure you've got to do the 5-step method on the exam. That's really what it's for. All the 5-step method stuff that you've been practicing on the homeworks has been to practice for the exam. And again, remember, I know that you know the answers on the exam. It's not about who has the answers. That's not what it's about. It's about how did you get to the answers. And the 5-step method is your like minimum guide for doing so in a way that I can follow. So here's my step 1 DFP for the big old duck problem. It's a little much. I should have used more than one color, which I would highly recommend. But I've got the duck going across, at a height of 40 meters. Excuse me. I basically more or less, I'm copying the diagram that was provided in the problem, but I'm adding some things to the diagram. First of all, I'm adding coordinate axes. I'm making it clear. I'm labeling that along the horizontal axis, I'm going to say that anything going to the right is called positive, and anything that's sorry. Was that me? Wait.
Hello.
Oh, weird.
Hello.
Wait, sorry,
Okay,
hold on.
hello.
Also, that just reminded me of
Good afternoon.
Whoa,
that's
whoa,
two.
that's
Thank
really
you.
weird.
Good
Sorry,
afternoon.
hold on.
I'm going to say this.
That's
before-
really, I don't know if you can hear that, but that's
Hello, Jamie. Good afternoon,
Wait,
Carla. Good afternoon, Michael.
wait.
Awesome.
That's
Thank you.
I don't know if
Wait,
you can
do I
hear that.
not
That's
see?
really embarrassing. Why is that
Yes, I
happening?
do. Okay.
Hold
And-
on.
And
Okay. God, as though one of me was not enough. Two of me. Jeez, Louis. Two. Yeah, that's bad. Okay, so I guess you could hear that. That is really bad. The only person that'd be more disappointed with that would be my wife. Okay, hold on. Now also, Melina, I'm sorry, I left you hanging for like 13 minutes. Can I go back to definition? Yes. You mean you want to see? So sorry. I knew it was something I should have just dealt with right away. You want me to go back to tell me.
The Form 5 definition, I just like missed the end of it. Sorry.
Oh.
Right there.
Oh, yeah. Okay, so it's yes, thank you. Right. Here it is on the front page. Yes. Okay. Sorry. Yeah. Good point. Okay, so Form 5 says, sorry. Oh my God, Amanda's like out of control. I'm really getting to know you people. By the way, don't forget, since I really am feeling like I'm getting to know you, which is good, and I'd be happy to write recommendations at any time when you need blah, blah, blah. But also feel free to visit me in general between 11 and 1 on Tuesdays in my office lab on the 4th floor, just saying, that's the best time to find me. And then we can all see each other in 3 dimensions. Anyway, yes, what Melita's asking. Here is the 5th form. It's English. It's not, it really changes our math. Believe me, it affects our math, but it itself, it is English. It's saying, in fact, let me correct one thing I was going to say is, it doesn't matter if you wrote it either way makes, but I'm just saying is in fact. So the principle is, or the form of the principle is every n-dimensional, and n could be any number, right? I'm saying from now on, this is true in physics in general. Specifically for us here, I'm talking 2 dimensions. I'm saying every 2-dimensional problem or experiment is in fact 2 1-dimensional problems happening at the same time, but independent of each other. And that really, those 2 words are the key. And like everything else, hopefully it sounds sort of reasonable when I say it, but it takes a while to sink in and really see in practice. And again, I'm glad so many people in your class like privately say things to me like, or in like your like video like summaries, you'll say, I get what you're saying, but I really need to see more practice with it. Totally, yes. So we're about to practice this with the big old duck here, but the key 2 words are simultaneous yet independent. That in the big, so hopefully that answered Melita's thing. Wait.
Yeah, you answered it. Thank you.
Okay, good. Okay, good. So I'm going to move, but also in the chat, I'm going to put, I see, where I live, it's 1 room now. I mean, it is a lab, it's a small lab, but it is my office, whatever. Where I live, and that's in the new building. 4th floor, very quickly for anybody who, 4th floor, it's so easy to find that it's impossible to find. Really quick, you go to the 4th floor, and it would be good if you want, alert me that you're coming just in case, because like I go back and forth all the time, but 4th floor, you come out of the elevators on the south side, i.e. on the men's bathroom side, you come out of those elevators and start walking to the right, like toward the jaywalk. Do not go into any of the back halls where all the normal labs and offices are. Like it's not in a normal place. You just walk to the jaywalk from the elevator and you will see what right before the jaywalk, there's 1 door just out there, like flying, where people hang out on the couches outside. There's just 1 door hanging right there. And you might not have ever noticed it, but then if you look, you'll see my name and stupid crap all over the door. That's where the 4th floor, right before the jaywalk, on the south side, for whatever it's worth. I would love to see any of you. But okay, so back to Melita's. So that's Form 5. Now, what this is going to say, specifically about the big old duck, form number 5, is we're going to look at this problem. I've labeled the axis. I'm saying whatever's to the right is positive and what's to the left is negative. That's one axis. Then I make an independent assignment. I make a plus and a minus like choice or assignment on the y-axis. Like it's 2 different worlds. They each have their own plus and minus. Right? And then I start writing down the facts that the problem gave me. Like the duck like moves for 20, is moving at 20 meters per second horizontally for a half second. And then as soon as it and then it speeds up. It starts accelerating after half second, presumably because now it's reacting to the fact that it heard a shot or something like that. So notice I wrote all the facts in here that were provided in the problem, but I'm starting to put in subscripts. I'm starting to make a distinction now. I'm saying like the V naught of the duck relative to the x-axis, right, compared to the x-axis or measured in the x-axis frame reference, V naught x is plus 20 meters per second, plus because I'm calling to the right positive, but V naught x is plus 20 meters per second. Whereas if you look down at the dude, or I forget what it's called, who's like shooting the shot, the initial velocity of the shot is V naught y equals positive 30 meters per second. Like I'm making a distinction. There's one velocity that's going on relative to this coordinate system, and there's one velocity that's relative to or measured in the other coordinate system, the horizontal. They're totally independent. They're not contradicting each other. They're both relevant, but they're both doing two things by themselves that aren't affecting each other. Okay, so I'm using subscripts now, like the problem didn't provide, but I am. And there's an acceleration to the right. AOX equals plus 16 meters per second squared. The acceleration in the y direction is constant. It's the acceleration due to gravity, which you're encouraged in this problem, and you're always encouraged to, since we're not in the lab, you can round it to 10 meters per second squared. I'm calling it negative here just because I've already assigned the downward direction as negative. Again, remember, like when you did the bolts problem, again, this is like Galileo in action here. Galileo is like the hard bit in a way. No one ever knows quite how to use it, but where you use Galileo is in setting everything up. It's how you make the decisions before the math crank starts churning. So for example, when you did the bolt A and bolt B problem, in that problem, that was hard in a different way, but everything was falling down in that problem. Nothing ever went up. Everything always went down. So there was only one direction involved there. So in that problem, we called down positive. There was no reason to call down net. We want as few negative signs as possible. All of us do. Negatives are there to distinguish from positive. But if everything's going one way, you make that way positive. So in the bolt problem, we called down positive, and therefore gravity, the acceleration, free fall acceleration, was the number positive 10, right? We make these decisions to make our life as convenient as possible. We're allowed to make them because of Galileo, but we have to make them also because of Galileo. So, all right, so here's my setup. This is step 1, DFP for the duck problem. So then the original question, step 2, WIQ, is, in effect, is when the problem begins, where is the duck such that the duck actually gets shot the way we want? So I'm going to make it even more clear. When I say t equals 0, and the more I can annotate, the more you can annotate. Your exam, if you do your exam right, your exam will contain all the information like that my solutions do, but it'll look very different, right? The more you start expanding, the more you explain things, the more each, just like if you have another professor, like all these notes of physics, they look different. The more you know what you're talking about, and the more you expand, the more it ends up just being your document. But so what I want to say right here is by t equals 0 means when the shot is fired, right? That's the stopwatch starts when the shot is fired. And the original question is asking, where should the duck be when that shot is fired? Let's assume, and I think it says on the other picture, assume that along the horizontal axis of the duck, assume that the y-axis is drawn along the line of the shot. So when the duck intersects, when the duck gets to the shot, we can call that position 0. And we're trying to figure out what negative position, how far back, how far to the left the duck should have been at the moment the gun was fired, such that the duck does get hit by the bullet from the gun, right? That's the question. You could phrase it however you want, but that's the question. So notice, before I even get rolling, if you really think about what the question's at, I mean, what's happening is something like this, shoom, right? Like, so it's two-dimensional. It's like this, but what we're really asking is where should this duck be horizontally initially, such that the duck and the bullet are located at the same point in space at the same point in time. We're asking about a collision. We want the duck and the bullet to intersect. So why I'm dwelling on that is if we want to now start doing this problem, like that's step 2. What is the question? The question is, where was the duck? Which again is just like lab 4, right? We're not predicting where the duck will be. We're trying to solve a crime, in effect. We're asking where was the duck if this crime, if this crime occurred, right? Just like you did in lab 4. So if I want to answer that, if I go to step 3 GDP, really the first thing I'm going to say as my GDP is this principle of relativity, is this form 5, the thing that Melita just asked about. I forgot, I wrote it again here. Because what we're assuming is that some physics is going to happen in this y-axis that we believe we have like equations to solve. And some physics is going to happen in this x-axis, and we believe we have physics equations, the same equations, to solve that. But we believe that what makes this one big problem is this physics is going to happen at the same time as this physics. When the stopwatch starts, at that moment, the shot starts going up along the y-axis, like time equals 0 means bullet has started to go, and the climb and the clock starts for the duck as well. Like we say, boom, we go click and bang, and the duck, who's already been going 20 meters per second at the moment, like hears bang and like takes it into consideration and like takes a moment to have reaction time or whatever. And then a half second from that bang, the duck starts accelerating. So the same clock is governing both these motions, but that's the only thing they have in common, or it's the only thing they need to have in common, is that they're being measured by the same clock. Other than that, they are their own physics. So we're going to solve them separately. What we're going to say to ourselves, we're going to say, how can I approach this problem? So I'm going up to the blue part on this page. The sub question that I have to think to solve now is, how much time would this shot take to get to traverse, it says to travel, whatever, traverse, to travel, well, to reach, I'll just say, to reach the required height. Like, to some of you, this is really obvious what we have to do first, and some of you, it's really not. Let me make clear. I'm saying the first thing I've got to solve for this problem is, if I shot a shot out of a gun at this certain speed of 30 meters per second, how much time, and I was near the surface of the earth where gravity is acting. The question I'm going to ask myself first is, how much time will it take this shot to arrive at the height of the duck, which is 40 meters up, I believe, right? Notice, I mean, in a way, once I say it, it's like maybe totally obvious, but many of us, if we look at this problem, like have no idea how to begin until you break it down. What I'm saying is the way to begin is to realize that we're going to divide this problem into a vertical situation and a horizontal. What's going to link the two together is the notion of time. So let's think about which of these two axes could possibly tell us anything about the time. Or put another way, which one, if you really think about it, one of these axes is going to dictate the time that the other axis is going to obey, if you really think about it. Now, I'm not saying in all problems it's always the same axes that are going to do that. But in this situation, like the reason we just did the practices that we did last Wednesday in class, the do nows and everything, if you think about it, at least the very last do now that we did then on Wednesday was we asked, like, how high would a bullet get if you, or a rock, we said, like, if you threw a rock up at 60 meters per second or something, like how high would it get and how much time would it take to get to a peak height and stuff like that. We asked a bunch of questions about a rock being thrown up on the assumption that we could just figure those out. And we didn't need no stinking duck to figure those things out. That's what's happening here. I believe that if I shoot a bullet up at 30 meters at some known initial velocity, I can in advance figure out how much time it's going to get for that bullet to get to a certain height, a height of 40 meters. And I don't care about the only role that the duck is playing in that question is that the duck dictated how that I come up with the number 40 meters. Like it's the duck's height that I'm thinking about. But other than that, the duck is not doing anything here. So what I'm going to do is say, oh yes, the y-axis, the bullet is going to determine how much time we have to work with here. We have a fixed amount of time that physics will force to get from this ground to this height. And then the duck is going to do a certain thing in that amount of time, according to physics. I'll move on. But I'm just saying, if I think about it in this problem, time is what links the two axes together. I'm going to treat each axis independently, but I'm going to make a choice from the outset that I think I can learn about the time from the y-axis. I think the y-axis is what's going to, in effect, determine the time. I'm going to warn you right now, if you're still with me, I'm going to turn the page, obviously, but what sometimes happens on the exam is you get a problem very much like this, but we tweak it. So it's like all the same type of problem, but that sometimes on the exam, it's the other way. Sometimes something in the horizontal axis will determine the time. And then you use that time in the other axis. So like you have to think, but here I go. But so that's just a side. So maybe that's even true in the practice exam that's scheduled now. Like we often, if you see a problem about the Roadrunner or the Coyote or something, which I think is the problem in if you'll know you're understanding something if you start to recognize that the Roadrunner Wild Coyote problem is the same physics as this. It sounds like a different problem, but once you realize it really is the same physics as this, and if you see that, you'll know that you're making some progress in this class. But anyway, here we go. I'm going to solve for the time of the bullet to reach a height of 40 meters if it was thrust at an initial velocity of 30 meters per second. This is not supposed to be negative, it's supposed to be an equal sign. Okay, so this is just a physics problem, and assuming that we have gravity going down at negative 10. So I'm saying this y-axis, I'm going to solve a physics problem in the y-axis just as though it was last Wednesday. It's unaffected by anything the duck does. The only role the duck is playing is that the duck is 40 meters high. That's so here it is. Excuse me. So I set up that equation. I think that this is a good equation. I mean, I know the displacement vertically. I know the acceleration. I know the initial velocity. I don't know the time. This is a pretty good go-to equation when in doubt in these kind of problems. So you could, and you, again, if this were the first time you were taking the exam, something you might write down some other equation first, like average velocity equals displacement over time. That's a definition. It's always true. If you wrote that down first, you get points for the fact that it's true. But then you would look at it and realize you have other facts you need to deal with it. You would realize it's not going to do that much for you. So you write another equation down. You don't like everything you write that's true is good. But this is the one I came up with. All right, so the ground I'm calling 0. So I'm trying to find out, well, you'll see what I did. So I just plugged in the values that I had. Notice I'm very careful now about pluses and minuses. Like the thing is being displaced up, the bullet, the shot, whatever you call it, the rock thing is going up. So that's a positive displacement, but it's being accelerated down, like gravity is pulling it down. So in this context, gravity produces a negative acceleration, but it does have an initial velocity. Another thing too, this is an example. Don't think that initial velocities are automatically 0. Initial positions are usually often 0. If you can get away with calling wherever an object starts the 0 place, we generally, as long as we only have one object in mind, we can generally get away with that. But objects do not necessarily start with 0 velocity. If they started with zero velocity, they wouldn't go anywhere probably. So this thing started with the initial vertical velocity of 30. Also notice, I'm sorry, last thing, the equation that I wrote at the top, it is just that standard equation that we started practicing last week, we established 2 weeks ago, but I've put subscripts on it now, right? I'm trying to tell myself that's an equation that is true in a line. It could be true in this line, or it could be true in this line, but it's going to give me different numbers, different results, depending on what line, what axis I'm in. So I'm just denoting to myself that I'm with reference to the y-axis here. That's why I put y subscripts on it. It's just the same old equation. Okay. So I set it up. T is the unknown. So now it seems like I have a quadratic to solve. Well, that's annoying for those of us who hate quadratic equations, which is many of us. One nice thing about it is it shows like, you know, that quadratic formula that you once had to learn that seemed like you would never ever be meaningful in any aspect of your life. It turns out it actually is pretty meaningful. You could solve this thing with the quadratic formula now and finally, you know, like wipe the rust off that thing. Or you could punch this into a graphing calculator. That's fine. You're obviously allowed to use calculators on this exam. Or you could hope that we often try to make these numbers not unreasonable. So we try to come up with numbers here that would make this thing factorable. So I happened to, oh God, sorry. Hello. You can solve it any way. But I like to factor when oh my God, I like to turn the page. Hello. Okay. So I factored it and I got t minus 4 times t minus 2 equals 0. You know, even if you don't like factoring, you can go backwards. You could check that my factoring is right by foiling it, you know what I mean by foiling. So I got t minus 4 times t minus 2 equals 0 now. And I know we have 24 minutes left. This is interesting now. Now, like I'm in math land here. And this is, by the way, somewhere I forgot. This is all step 4, PAW. I don't know. I wrote that somewhere. Well, maybe I didn't write that. I mean, I think at this point I'm in step 4 PAW. Sorry. Because now I'm like plugging in numbers. Oh, I did. Yeah, step 4. Okay, it's step 4 PAW. Okay. Now I've lost it again. Okay, sorry. Obviously, this is a new. Hello. I know. Don't try to trick me. Okay. I don't know. Why can't I turn the page? Okay. All right. So I factored it. So I'm just doing math now, but I got 2 answers. Now, everybody knows in math, everybody knows. We may be comfortable that in math, when you have a quadratic, you get 2 roots. That is, a quadratic is like some sort of parabola. It often crosses the axis at 2 points. So there's 2 answers to a mathematical quadratic. But this is a physics problem. And we just got 2 answers. Now, first of all, they're not answers to the whole problem. Right now, we're in a sub-question. We're just solving for how much time does it take the shot to get to a height of 40 meters. But we got 2 answers. What are we supposed to do with that? We're supposed to take it seriously is the answer. Math is the language of physics. If the math spits out 2 answers, that means that there are 2 physically meaningful answers. Sometimes, and so you can't just like throw one of them out, and you shouldn't, definitely not in this problem. Sometimes it is the case that the math gives you more than one answer, but the way the physics question was worded in English, we sometimes know in advance that we might only be interested in one of those 2 answers, maybe, sometimes, depending on how the question's worded. But all the answers the math gives us always mean something in the physical world. And in this case, these both definitely mean something, because the question that we're solving for right here, what we've told the math is, we want to know, given certain facts, we want to know how much time will elapse from the moment the gun is fired, the slingshot is fired, to the moment that the bullet is at the height of 40 meters, given that it's shot up and given that there's a thing called gravity, which is always accelerating it negatively at 10 meters per second squared. Well, given those givens and given that question, the math is absolutely right to tell us that there's 2 answers, because actually, does someone want to? Oh, you're in the chat. You're totally in the chat. You guys are awesome. Wait. Yeah. Okay. Remember. All right. So since at least so yeah, the quadratic would give you right. Plus or minus b. I mean, negative b plus or minus the square root of b squared minus 4ac over 2a. All right. So that would definitely. So if Amanda or Chris or anybody wants to answer, like, why physically here in this case, why the heck should there be two different times that are both validly true for when this shot reaches a height or is at, I should say, why should there be two different times at which we would see this shot to be at a height of 40 meters? Like, it's not a trick question, but it may be a tricky question. What does anybody know? Like, I'm saying literally we have to take both that 4 and that 2 seriously. Those are both potentially correct for the amount. Oh, no, I don't see it.
Can I answer?
Please, yes, I'd be thrilled.
Okay, because what I'm thinking, right? It's like, let's say because we saw for the time, the 2 roots of time. So let's say you fired a shot like in 2 seconds. That can imply that you actually shot the bird within like the first shot. But like, if you shot the bird 2 seconds later, so at 4 seconds, you could have missed the bird. But if it's like the shot can come up and hit the bird back down, if that makes sense.
It does make sense. I was hoping you were going to. Oh, yes, that makes sense. Yes. What I mean is, yes, good. Yes. Absolutely. And that's not, and it even sounds like even he is like being polite about it, like if it makes sense, whatever. But that's not a technicality. That isn't some weirdness. I mean, it might seem, well, I don't know what it seems like, but it's totally valid. Let me back up for a second. Remind us. So good. I mean, that's very good. And you should definitely submit for points for that. See, that's what happens if you guys eat later in the day. Then your brain is still, no, okay. Remember, this thing is shot up at a positive, like upward pointing velocity of, I think, 30 meters per second, right? And then the gravity rule, the acceleration, says that every second this thing loses velocity. Velocity is a vector. It could be plus or minus, right? I mean, it has direction. The gravity rule, the acceleration, says that we are every second losing 10 meters per second of velocity, and we're doing it forever. So if you take acceleration seriously, the velocities will go like this: positive 30, positive 20, positive 10, 0. And then if you take acceleration, if gravity is always there, if gravity is always robbing us, always reducing our velocity by 10, if it's always negative 10, right? So it went positive 30, then subtract 10, positive 20, like imagine you're making a chart, subtract 10, positive 10, subtract 10, 0. Now, if gravity really doesn't change its behavior, if the acceleration really is constant, now we got to lose 10 again. But how do you lose 10 units of velocity if you're already at 0, if you've already come to rest? Well, the answer is you go into the negatives because velocities can and do and must. So now you go negative 10, negative 20, negative 30. Think about this for a second. I mean, of course, I'm saying what Chris is saying. And of course, part of me is saying what everybody already knows, that what goes up must come down. Like, of course, the thing is going to go up and then it's going to come down. But now think about the numbers. When we say something goes up and then comes down, what we're really saying is its speeds are getting lower and lower and lower and then higher and higher and higher, right? It's slowing down, slowing down, slowing down to rest and then speeding up, speeding up, speeding up. Now, I know all of you know that, right? And we sort of like thought about that last week too. It's going like in terms of speeds, in terms of magnitude. And a couple of people in the other class really wanted me to say this like 4 times an hour ago. So like definitely like make a note of this or whatever. I'm saying speeds. And I think it also asks about this in the practice exam, actually, or the old one anyway. The speeds are going like 30, 20, 10, 0, 10, 20, 30. The speeds are, the raw numbers are going lower and lower and then higher and higher. So the thing is slowing down and then speeding up. That's what the speeds are doing. But for that reason, a lot of people make mistakes or get confused and then think that they've got to change the gravity number or change the acceleration value, like depending on whether you're moving up or moving down. A lot of people get very confused and think like they should make the 10 like negative when you're on the way up and then make it positive or something when you're on the way down. No, no, no. The acceleration refers to changes in velocity, not speeds. So the velocity numbers are going like positive 30, positive 20, positive 10, 0, then negative 10, negative 20, negative 30. Note, if you write those down and just really think about it, the velocity numbers are always going down. The acceleration is always negative. Gravity is always pulling you down to the ground. It's following a consistent rule. You're always subtracting 10 from your velocity, whether you're going up or whether you're going down. Last way I'm going to put it, whether your numbers are getting decreasingly positive or increasingly negative, they're always subtracting, subtracting, subtracting. So the velocities are always getting lower. The acceleration is always negative in the way we're saying it here. But therefore, what that means in English, if you stand and look at the thing, like Chris said correctly, like the thing is slowing down on its way up, and then it's going to come back down and speed up. And there's nothing in this physics that ever said the duck has to be hit like while the bullet's on the way up. It's perfectly valid. Like Chris was very polite about it, but and maybe it seems like it'd be tricky, but if you really think about it, depending on where you put you could put the duck in one of two places. This is saying, I will move on. I know there's 14 minutes, but it's saying like, look, if you put the duck close, then you're going to have a simple, obvious collision like this. But if the duck is really far away, it's not like you have to do anything different. You don't have to do anything tricky. As long as you put the duck in the right space really far away, then your bullet's going to go up and up and up before the duck ever gets there. And this is just what Chris is saying. I'm just expanding on it. Like if you put the duck really far away, then your bullet's going to go up and up and up and up while the duck's coming in. And then your bullet's going to start coming down. And then they're going to meet when your bullet's on the way back down. And that's no worse than hitting it on the way up. It's also shouldn't be any harder if you really think about it. If you're really trusting all this physics, it's the same thing. So what I'm saying is the physics, the math correctly said there's going to be two different times we've got to solve for. So when I go to the x-axis and start plugging in times, I'm going to plug in two different times to get two different final possible answers of where this duck should be. One would be a close position where the duck would get hit on the way up, and the other would be a far position where the duck would get hit by the way back down, and they're both equally valid. Okay, one last thing I want to, I am watching this. That was great, Chris, and anybody else who did understand. I'm hearing Chris. Oh my God, that is funny. Wait, yes, that you're hearing correct. But wait, what's Amanda saying? I know you got ad. I'm talking about the ad. Wait, sorry. Maybe this isn't. Oh, there's a lot that I missed. Oh my God, wait, there's a lot. Wait, I do want to see the chat. I'm sorry, because some of this is legitimate physics. Because a lot of the right, Amanda, right. Never mind, Chris has a real okay. Oh, you are guys, they are actually nice to each other. If you play Bo, maybe I don't. Oh, so there's a game based on this. Maybe you should send me a link to. I would like to see that. I don't know that game. I do know many games, but oh, that's cool. Okay, wait, that's very cool. I may want to check that out, or my son might like. I mean, especially if it's like free on anyway. If anything that's not any moment spent on any game that isn't Fortnite, I'll pay money for in this house. Okay. So one last thing I want to say about this, we will get an answer, I promise. Is again to emphasize how much all of this is just saying the bullet is just doing physics. The bullet does not care about the duck. The physics that the bullet follows is not affected by the duck. The only role that the duck is playing so far, what we're solving is that the duck is at a certain height, and that's the height we're trying to get at. So much so that what I could do for practice, the very bottom line here, maybe it says it on the next page. For practice, I could say, wait, you know what? If there really was no duck and I shot something up at 30, how much time would it take to get to its own natural peak height? Like, how much time is it going to take before it falls back down? And by the way, I could be checking while doing that, like, is the duck high enough for this to work? Like, I mean, I hope the bullet will reach the duck. I mean, I hope Chris is right, like, let alone come back. Like, what if I didn't shoot it hard enough to even get to that height? Well, I can test just like we did. Yeah, on the bottom of the page. Well, yeah, okay, so here's an expand. This is everything I just said. Like if T is the time at which the shot is located, the shot finds itself at Y equals 40 meters, then those two possible times are 2 seconds and 4 seconds. This is just summarizing what everybody just said. 2 seconds is the way up, 4 seconds is the way down. But then it says, no, in blue, if we're truly calculating this independent of the duck, we could consider or predict or check ourselves. We can look at what the peak height would be. And if you think about it, I wrote equations here at the bottom that you could copy and practice to make sure you understand the equations. But really, the equations just capture just thinking about it like we did last Wednesday. I mean, the thing is shot up at 30 meters per second. It's losing 10 every second. It's shot at 30. I'm not trying to be, but like eventually you start seeing that all the equations are just symbolizing what's in our head already. It's got to make sense. It's not BS. You shoot the thing up at 30 and it's losing 10 every second. Well, it's like if I'm walking around with 30 eggs in my basket and I lose 10 every day, how many days does it take me to fully run out of eggs? And the answer is 3, right? I mean, 30 divided by 10. And if you just do the equations carefully, you see that's what you're doing. So this thing has 3 seconds to get to a natural peak height. 3 seconds. Doesn't that make sense? That's directly equidistant between 2 and 4. In other words, when it gets to 2 seconds, when it gets to the height of the duck, it's got 1 more second to reach what would have been its natural height. Then it reaches that natural height and it's got 1 second to come back. It's perfectly symmetric is what I'm saying. The up trip is symmetric with the down trip because the acceleration is constant. I won't overdo it. But if you're really with me and you're getting bored because you know all this, you could also in your head, for practice, in your head, you could figure out how high the natural peak of this thing would have been. Like, I know it's going to get hit by the duck one way or the other. I know the duck is low enough to be hit because in my head, I'm saying to myself, this thing got shot up at 30. It's going to go and go and go naturally until it runs out, till it hits a velocity of 0. Right? So it starts at 30, it's going up and up and up till 0. So on average, I'm just going back to what we did on Wednesday. On average, if it starts at 30 and it ends at 0, on average, it's going 15 meters per second. It's an object which is on average going 15 meters per second. It would do that for 3 seconds. So this thing would travel 15 meters per second times 3 seconds, 45 meters, right? That's a little bit higher than the duck. How much higher? 1 second. How many meters? 5 meters. You get what I'm saying? If you don't, if it's too much, it's okay. I'll keep going. But if you see, it all is connected in the end. You will see that the easier physics gets, the easier physics gets. Like the more you start seeing that it's all the same and you start getting bored, you'll realize, oh, you get it. It's all the same. But okay, wait. Oh, if you stand underneath, and I'm going to keep going, but yes, genius. I mean, Chris. No, yeah, if you stand underneath, you're definitely hit by it. And this used to happen on New Year's Eve, like in New Orleans, where I first taught physics many years ago. Yeah, like dummies on New Year's Eve. Yes, if you stand right, yes. Bad thing to do. Don't stand under the bullet unless you definitely have a duck to protect you. No, you're right. Okay. So, but I know.
Here's a question.
Oh, sorry. Yes, please. Yes. Sorry.
So because we had the 2 numbers is why we did the velocity over time equation.
Oh, like
Like,
why
how
did that?
do we get-
Oh, at the bottom, the reason I did the equation at the bottom was just actually to check. I was just checking. I was trying to convince myself that those 2 numbers really kind of make sense. The velocity equation that I did at the bottom was to find out what the peak height like would be if no duck was involved at all. So I got 3 seconds, and that it was like a check. It was a check to say, oh, the height of this whole thing is at 3 seconds. So it kind of makes sense that 2 is when the collision would happen on the way up, and 4 is what would happen on the way down. Just it's like a check to say, oh, isn't that nice that 2 and 4 are like equidistant from 3, like. They're like mirror images of each other around 3. It's not, if you were solving this on the exam, that last bit that I'm doing on the page in black at the bottom, you don't have to do that. It's like a check to make sure that to see that if you like those answers. Like it is a check. It's good. Like if, in other words, if I hadn't gotten 3 at the bottom, I would think something's wrong with my 2 and my 4. Does that make any sense?
Yeah, thank you.
Okay, no problem. Okay. All right. So I'm looking at it. Okay, so we have 6 minutes. So okay, so all that now, by the way, I mean, I'm talking a lot. What else is new? But I think the part that we just did, what we just did was we focused on the vertical part of this problem, the y-axis. I think it's the hardest part. Like from here on in, it's pretty fast. It's hardest because first of all, we have to know to deal with one axis at a time. Like we really have to understand that. Like, and that's what happens in physics. Like things look like a lot, and you have to know that you can break them down into one piece at a time, and the different pieces don't affect each other. So first we decided to break it down into two axes. We'll always do that from now on. Second, we decided to look at the y-axis first. That was a choice because we think that the y-axis determined the time. In worst case scenario, if you're taking an exam and you have to think which one is going to determine the time, you might start analyzing one of the axes, and then you might realize you don't have enough information. You might seem like you're missing two things, the time and something else. Then don't panic and don't think that you're like a bad person, or just leave that and say, oh, maybe I should try the other axis. And eventually and then you'll be okay. And whatever you got so far on the first axis will become useful. Like that's whatever, that's just a test taking strategy. But when you hit a little wall, don't bang your head against it. Just walk around it or through it or whatever. Anyway. So what I'm saying is now we're going to switch over to the x-axis. We use the y-axis to get the key information, which is really how much time is this experiment going to take? And we found out, well, it's either going to take 2 seconds or it's going to take 4 seconds. Both those are valid. So I'm going to play out both of those numbers now. So we're now going to go, so the link between the two axes is time. So I'm going to use those times that I just got to now plug in to the x-axis. Now and I know I only have 4 minutes. We're basically, like the upshot is we're just going to plug in that time or both of those times into equations that apply to the x-axis. Now the x-axis has this funky detail that's just kind of annoying. What the x-axis story in this case is that the duck first is going along at constant velocity for a half a second, and then it like reacts to the noise or whatever, and then starts accelerating for the rest. So the duck really has two motions in the x-axis. It does two things, two different accelerations, two different equations, but we're just going to add the results together. Like basically what I'm doing here, to summarize quickly, is first I'm looking at that first look at the 0.5 seconds of constant velocity, right? So even if the only equation that I trust in the world is this 1/2 AT squared equation, even if I just used it on the y-axis, it did good things for me. So I tried again here, but I noticed that in the first part of the duck's motion, there is no acceleration. So it doesn't mean it's the wrong equation. It just means I call A 0 and that term crosses out. And then I find that I have a pretty simple equation. This is exactly like lab 4 here. You may recognize. The thing is moving at a constant velocity in the horizontal axis at first. So I just plug in the velocity that was given, which was 20 meters per second. And I multiply by the time that was given, which is a half a second. So what I find out is first, the duck goes for 10 meters, no matter what, like the duck has to, so I've got to put the duck back at least 10 meters. The duck is going to travel 10 meters in the first half second of this experiment, no matter what. But then there's more time left over to deal with that he's going to accelerate. How much time is left over? Well, either 1.5 seconds is left over if I'm using my 2 for the whole thing, or 3.5 is left over if I'm calling 4 my time for the whole thing, right? Like here's where the 2 and the 4 come in. They mean that I've got either 2 seconds to play with for this whole experiment, or I've got 4 seconds because that's how much time, is ticking away while the shot goes up. So I subtracted a half second from that just because the problem has this annoying detail that for the first half second, the duck is just doing something simple. So what's left over is either 1.5 or 3.5. So I take each of those times and I literally plug them in to that same equation that I was using before, but now I'm in the x-axis. So like now I'm doing x minus x naught equals 1/2 a sub x times t squared plus v naught sub x times t, right? Same thing as before, just all the x information. What's v naught x? It's 20, because the problem told me that. The thing was initially going at 20. From the moment it starts accelerating, and it's accelerating at positive 16, positive because it's accelerating to the right, the problem said. So I just plug in each of these and I get answer. Right? I know I'm going a little fast right now, but just notice I'm doing physics on the y-axis and the same physics on the x. The only difference is on the y-axis, I did physics equations to solve for the time, and then I use that time and plug it into the x-axis because that's the link between the two. So when I just plug in, I get numbers like for the x up, I get like 30 meters. I mean, for x, if I hit it on the way up, the shorter distance, I get 30. For the larger one, I get 168. But then again, there's just this like annoying small detail that, by the way, if on the exam you forgot this one detail, it'd be like 2 points. It's not the big thing, but it also did do that additional 10 meters either way in the first half second. So my two answers in the end are like 40 and 178. So to answer the actual original question, for the duck to be shot, and it's 420, I'm just finishing the sentence and we're good. The duck must either be placed back 40 meters, like to the left of zero, i.e. I'm calling it -40. It's either going to be at -40 if I want to hit that duck on the way up, or it's got to be placed at -178 if I want to hit it on the way down. Those are the two answers to the question. Question part C says, could there possibly be 4 answers? No, there couldn't. Worth talking about on Wednesday if you remind me. But no matter what, there's only 2 routes to a quadratic. There's only 2 possible ways you could hit this duck. But if that confuses you, or you think you could remind me on Wednesday, we could talk more about it. But I'm done. Hopefully this was helpful. I think you guys, I'm really enjoying this class. I'm enjoying all the banter from all of you. It's good. The banter and the substantive questions are great. I will hang out. If anybody has any questions, I'll be there tomorrow in my office at 11. But you should go if you. So thank you very much.
Thank you, Professor.
Thank you. Thank you, Elwell. Have a great day. Thank you, Michelle. Thank you guys. Thank you. Hi, you and Michelle for coming. Thank you. Thank you.
Thank you, Professor.
Thank you, guys. Thank you. I'll turn them stuff. That was a great question, Melita, and great contribution, Chris and Michelle. Oh, and Amanda. Is Amanda still there? She turned off. Anyway, I'm going to turn. Okay, I'm just shutting.